The senses delight in things duly proportional. That fundamental truth of aesthetics is as meaningful today as it was back in the 13th century when Thomas Aquinas mused about our physical world. He was expressing the direct and very often measurable relationship that exists between mathematics and beauty, a relationship that applies both to natural beauty and to man's art. This kinship falls into the sometimes exotic domain of geometry. Spheres, circles, lines, curves, and triangles can be found in many natural things. These shapes represent the simple and straightforward alliance between mathematics and organic beauty. But to fully appreciate their long-standing and mystical romance, we need to look at more intricate designs of shape and form. The spiral is one of nature's favorite forms of mathematical expression. For anyone looking at a sunflower or a daisy, the tiny florets arrange themselves into spirals. The eye sees these spirals as two distinct sets, one radiating clockwise and the other counterclockwise. Furthermore, the heads of these flowers are made up of a fixed number of spirals. Large sunflowers have 89 spirals going in one direction and 144 going in the other. Many daisies are made up of 21 spirals and 34 counterdirectional spirals. Pineapples exhibit a sort of three-dimensional spiral pattern, 5 going this way, 8 this way, and 13 this way. Arrangements of leaves, scales, and the flowers of many plants display spiraling. The nautilus shell also illustrates this notion. Its logarithmic spiral growth pattern is determined by adding elements of the same shape as those already present, but of a different size. This natural phenomenon of opposing spirals commands a fascinating and mysterious place in mathematics. In 12th century Italy, a mathematician named Leonardo Fibonacci described a series of numbers starting with 1, 1, and adding the last two numbers to arrive at the next number, such as 1, 1, 2, 3, 5, 8, 13. By adding 8 and 13, which are the last two numbers, we can find that the next number in the so-called Fibonacci sequence is 21. The next is 13 plus 21, or 34, and so on. The numbers in the Fibonacci sequence correspond to the number of spirals found in any spiral growth pattern, like the sunflower or pineapple. The pineapple spiral ratio of 5 to 8 to 13 corresponds to adjacent Fibonacci numbers, as does the sunflower's 89 to 144, the daisy's 21 to 34, and the pine cone's 5 to 8. No one is quite sure why this ratio occurs so uniformly in nature, but that it does is only the beginning of our mathematical mystery. The Fibonacci sequence also appears to exert a strange influence over art and architecture. The ratio of any two adjacent numbers in the series, larger than 3, is always about 1 to 1.6. Euclid called this the golden ratio, and for centuries since Euclid's time, the golden ratio has intrigued mathematicians, artists, and architects alike who've linked it inextricably to aesthetics. The ratio occurs most notably in what's called the golden rectangle, a figure whose sides bear the magic relationship of about 1 to 1.6 to each other. For Leonardo da Vinci, the great Renaissance artist, scientist, and inventor, the golden rectangle is represented in his drawing of an old man. Most probably a self-portrait, Leonardo overlaid his picture with a square, subsectioned into rectangles, some of which illustrate the golden ratio. Some art historians and mathematicians believe that the golden ratio may have guided his sketching, but no one's really sure if the rectangles follow the proportions of the face or govern them.
One of the interesting things about the painting is that there's a kind of simplicity where the artist is looking.
Associate Professor Dominic Cretara teaches painting and drawing to students at the Art Institute of Boston.
So you have this series of light. Leonardo was not satisfied with applying someone else's principles, and he made an exhaustive study of the human body, where he made calculations of the proportional relationships of the figure in great, great detail. In fact, he talks about the relationship from the eyes, the top of the eyes, to the point where the lower lip meets the chin, to the point of the angle of the back of the jaw to the top of the ear as inscribing squares. He talks about the fact that a man sitting down, kneeling down, diminishes his height by 1/4. There are all of these specific observations which are related to mathematical proportions, harmonies, that he discusses in great detail in his work. And therefore, he says, arithmetic and geometry tell us truths about quantities, and they tell the truth about these things. So that for Leonardo, it seems that visual sensual experience, knowledge derived from the five senses, when mediated through mathematics, becomes certainty. Leonardo did say in his writings, he wrote that let no man who is not a mathematician read my elements, which is somewhat foreboding introduction to some of his writings, but I'm sure he meant it literally.
Leonardo's fascination with Euclidean geometry led him to study optical theory. In due course, he found the reason why, and I quote, "A second object, the same distance from the first as the first is from the eye, will appear half the size of the first, though it be the same size really." Today, we call this quirk of art and nature perspective, the quality which gives an image a three-dimensional depth. Euclid was primarily interested in the world as it is, in 3 dimensions. The artist Leonardo's interest was piqued by linear perspective, which deals with the methods used to draw 2-dimensional pictures of our 3-dimensional world. In appearance, an object may seem very unlike what it is known to be in reality. The most familiar example of linear perspective is that of railroad tracks. They're the same width throughout their length, yet in appearance, the rails seem to approach one another in the distance. The point at which the rails seem to meet is called the vanishing point. In order to draw linear perspective, Da Vinci was one of the first to fashion a viewing contraption that allowed him to record the proper perspective of the subject. Called Leonardo's window, it required an artist to be not only creative, but a contortionist as well. In order to use one, I have to close my left eye, rest my head in my hand, keep my right eye fixed so that I can look at the subject that I want to draw through this vertical sheet of glass. Now, a straight line coming from the subject to my eye represents a ray of light reflected from the subject to the eye. So the intersection of that line with the sheet of glass corresponds to the apparent position of the real point of my subject. Okay, now if I can keep my head fixed and mark on the sheet of glass, I can draw all of the points like this. Join them up with lines and get a true perspective picture of the subject. Do you think Leonardo really started that way? Although it was a great help in its time, Leonardo's window is a fairly awkward way of drawing linear perspective. Fortunately for us, there's an easier way.
When you have a one-point perspective situation, we are always facing the side plane of in this case, the block. You're confronting the face of the object. When you're drawing in 2-point perspective, we are normally facing the corner of an object. Now,
Nathan Goldstein is a professor of painting and drawing at the Art Institute of Boston.
Now, as these 4 lines cross, they create 4 points. And once again, as with the example below, we can construct 4 verticals. And this can be of any height. Let's make it, in fact, a little bit higher. We'll go above the horizon line. Remember, that's your eye level. Referring to our points at the horizon line, we just have to hit them. And once again, we've constructed a block. And this time, put some tone here. This time, we're looking at the corner of the block.
The search for harmony of proportions is a consistent theme throughout art and mathematics. And to get the proper perspective, so to speak, we have to address the notion of symmetry. Depending on how narrowly or widely we try to define it, symmetry is one idea by which man has tried to comprehend and create order, beauty, and perfection. In an aesthetic sense, symmetry implies a balance between left and right. This common notion of balance, as illustrated by the print we're making, is often called bilateral symmetry. If we draw a line through the center of the print, the top and bottom halves are mirror images of each other.
You have several axes of symmetry moving.
Symmetry is used by anthropologists to classify and identify the pottery and artwork of various cultures. Dorothy Washburn of the University of Rochester in New York.
It's a simple geometric fact. It's part of the geometric world impinging upon the cultural world that anytime you repeat something systematically, you'll find some of these symmetries. But people, for various reasons, which we don't know yet, preferred certain kinds of symmetries in certain situations. Certain arrangements apparently were very comfortable for them, and they used them over and over again in many aspects of their life. Likewise, using the same symmetry, the same arrangement of their motifs, allows people to recognize the patterns as theirs and to use it for their, as markers of their own culture.
Astoundingly, after studying and classifying many patterns in terms of what kinds of symmetries they have, it became clear that there are only 7 distinct one-dimensional repeating patterns, those that can be designed along a strip or a band. Contemporarily, you can find these patterns in a place as close to you as your own home. If you have a wallpaper border between your ceiling and the wall, then you also have an example of a one-dimensional repeating pattern. In fact, any one-dimensional repeating pattern found anywhere in the world will always be one of the 7. We can demonstrate the symmetries found in these patterns by applying 4 different tests or transformations: translation, rotation, reflection, and glide reflection. We'll use generic symbols like commas to design our patterns. Each of the 7 patterns illustrates the first kind of symmetry, translation, which is simply a shove or push in some direction for a certain distance. As we can see, any one of these 7 one-dimensional patterns can be pushed to the left or the right without appearing to have moved at all. 3 of our patterns, 4, 5, and 7, also admit to our second type of symmetry, rotation. If each of these patterns pivots around a point in its plane by 180 degrees, the pattern in its new position will look exactly as it did before the rotation occurred. A reflection can be found in pattern types 6 and 7 horizontally and 3, 5, and 7 vertically. Using number 7 as an example, we can place a mirror horizontally along the pattern or vertically across the pattern. Since reflection is present, we can still see the whole image of the pattern because the visible half will be reflected exactly in the mirror. We can also imagine folding the pattern along the mirror line. The result is the same. The 2 halves will match exactly. Symmetry obtained through reflection is the formal geometric name for bilateral symmetry. As I've said before, when most people mention symmetry in the general sense, they're referring to bilateral symmetry. The last transformation, a glide reflection, is a combination of a glide or translation and a reflection along some line in which the glide took place. If pattern 2 glides from left to right this far, it will appear to be upside down from its original position. But if the glide is followed by a reflection horizontally through the middle of the pattern, it will look the same as it did originally.
In other words, if we took this design and just rotated it 180 degrees, the design would really be the same.
How can the symmetries resulting from the 4 transformations help to classify and identify repeating patterns? By determining how many, if any, of these transformations can be used to describe the nature of the pattern. Since transformations are universal, they can be applied to patterns found anywhere at any time.
It's very important to have this non-biased classificatory system because one can do very systematic and objective cross-cultural studies. And that's been one of the kinds of things that anthropologists have wanted to do for a long time. Before, our descriptions of design have been largely idiosyncratic and dealing just with the individual type of material, like the type of textiles or the type of pottery. But now we can look at the way the motifs in the design are arranged and look at material from all different cultures all throughout the world irregardless of whether they're contemporary cultures or past cultures, and see how these designs are put together. And was interesting how they change through time and space.
Well, we've explored the archaeological significance of patterns, but it doesn't stop there. Modern wallpaper designers and textile manufacturers are very involved in the development of new patterns based on old mathematical rules. National Gypsum's Executive Director of Style and Design, Arthur Glazer, has been designing repeating patterns for over 40 years.
Everything we do has to be worked into a repeat of some kind. And the pattern is basically, it's what rhythm is to music. The pattern repeats and it sets up a rhythm. All right, this is a medium scale pattern, and I'll try to point out the repeat. From here to here would be a repeat, and looking straight across the sheet, we see the same element picked up here again. This would be called a drop repeat, and the reason for it is that the same element halfway down, or dropped down, repeats again over here, and it's also halfway across the sheet this way. The exact same thing is happening here. Here's the element repeated. Again, halfway down, it's repeated again, then picked up again, and so on. A larger pattern, but exactly the same elements. Here's one of the piece of design. Here it repeats again, and it repeats again, but half dropped. This one, it's a little harder to pick up. The repeat is hidden, but again, if you look closely, you'll find the same element does appear. And again, halfway between them, the same element appears again. Once people are aware that every pattern has a repeat, they seem to find it everywhere they look. And if you start looking at patterns from now on, you'll see the repeats.
In order to achieve the continuously repeating wallpaper patterns, specifically measured cylinders are used during printing.
As far as the mathematics of the thing are concerned, a cylinder has a specific dimension. We use mostly about 4 repeats, and we'll say one of them is 19 inches. Well, any pattern that you choose to put on that 19-inch repeat has to fit perfectly in 19 inches. If it's one flower, that's fine. You just put it on there, and it'll repeat by itself every 19 inches. If it's 2, it has to be half of 19. If it's 3, it has to be a third of 19, and so on.
In the 1930s and 40s, artist M.C. Escher gave dramatic new meaning to the ideas and rules of filling a surface with design. He ingeniously fit his repeating patterns together in such a way that he covered a plane without leaving any gaps. Now, completely filling a plane with small squares isn't too difficult, but trying that with more unusual geometric shapes seemed nearly impossible. One of Escher's most impressive works is Angels and Devils. Every point of the plane belongs either to an angel or to a devil or the curve where they meet. The pattern, regarded as repeating so as to fill and cover the whole plane, is symmetrical by quarter-turn rotations at each point where the wingtips of 4 angels meet the wingtips of 4 devils. It also exhibits reflections on certain vertical and horizontal lines. Much of the artistic mathematics we've talked about falls into the realm of Euclidean geometry, but Escher's work passed into the non-Euclidean geometries when he replaced a flat Euclidean plane with the surface of a sphere.
You make a difference when you pass from the Euclidean plane to the spherical plane or to the sphere. You still have angels and devils alternating, and you still have 2 angels' feet opposite each other and devils between them. But now the wingtips are differently arranged. You now have 3 wingtips of each meeting together at one of the points that's on the outside of the sphere.
Here's Escher's version of Angels and Devils in yet another non-Euclidean geometry, 2-dimensional hyperbolic geometry. To our Euclidean eye, the shapes appear to be getting smaller as they approach the boundary. But if you lived inside of this picture, there wouldn't be an edge, and as you walk along, the shapes stay the same size.
He, in that way, showed that one can compare things that happen in the hyperbolic plane and the Euclidean plane and on a sphere, and show the similarities and differences between those 3 kinds of geometry.
Representing this picture in 3 different geometries wasn't easy. Of the 3, hyperbolic geometry was the most complicated Escher had to master. The turning point came in 1958 when mathematical legend H.S.M. Coxeter of the University of Toronto helped out by sending Escher one of his own drawings.
I had drawn a picture like this, in which a circle is filled with black and white triangles, which are big towards the center and get smaller and smaller towards the circumference. And yet the triangles, although they get smaller and smaller, are all the same shape. This is a way of looking at hyperbolic non-Euclidean geometry, because if you can imagine that these triangles are not only the same shape, but also in some way the same size, as if there was some perspective foreshortening, then you get the idea of living in a 2-dimensional hyperbolic world. I feel that mathematics is an art, and that one should include mathematics among the arts just as much as among the sciences, and that one does appreciate beauty, and I think that many ideas in mathematics are in themselves beautiful. Patterns of numbers, patterns of shapes, they're all connected.
It seems almost poetic that as we learn more about the complexities of geometry, perhaps one of the most complicated of all, fractal geometry, brings us full circle, back to nature. By now, it shouldn't surprise us that nature is full of strange and beautiful shapes that repeat themselves in many different sizes. We saw the concept of self-similar shapes when we looked at how the nautilus and the sunflower grow. The leaves and the twigs of some trees have the same structure as the trunk and the branches of the tree itself. A boulder and the mountain it's chipped from also exhibit similarity. In fact, there are many patterns in nature that illustrate the same level of irregularity over a smaller and smaller area as we come closer and closer to them. Broccoli spears, lightning, mud cracks in a dry riverbed, snowflakes. The list is as diverse as it is long. But until quite recently, the irregularity of these shapes defied geometric description. They were known as mathematical monsters.
And 9.
Benoit Mandelbrot, a research fellow at IBM, has devoted much of his professional life to the study and description of these mathematical monsters. Known as the father of fractal geometry, Mandelbrot was the first to classify these self-similar yet irregular shapes.
A fractal curve is a curve in a plane which in some sense is between a line and the whole plane. Now a line is a well-known object. As you come closer and closer, it doesn't change, it's always a line. And the plane also, it's a well-known object. As you come closer, it's always a plane. But there are other curves which are in between, which again have the property that as you come closer, they remain equally complicated. They don't become simpler, don't become more complicated, just remain the same, except that you look at smaller details. And these curves are called fractal curves. This curve is not quite a line, it's wiggly, it goes away, but it doesn't go too much away from being a straight line. So you could say it's almost a straight line. Its dimension, it's a little bit more than the dimension of a straight line, which of course is 1. On the other hand, you can look at this other curve here, which almost fills the plane, not quite. It leaves the gaps in between. But this curve is, again, have this property. As you come closer, it remains unchanged. And this curve, you could say, has a dimension just a little bit less than 2. Now, these ideas, dimension a little bit more than 1 or a bit less than 2, these are very loose, intuitive ideas. However, it is possible to make them quite rigorous. It is possible to define a number which is such that is for a curve between 1 and 2 when the curve is in the plane, and this number measures the irregularity of a curve. And curves which have in this fashion a degree of irregularity which is between that of a line and that of a plane are curves which are called fractal curves. Fractals come in very many shapes and kinds, but for practical purposes it's very convenient to distinguish 2 purposes of fractal geometry. One is to imitate nature, to make forgeries of what we see around us, to make artificial coastlines which have the properties of actual coastlines, artificial mountains, or artificial clouds. And these are constructed by using what's called random processes. And on the other hand, there are fractals constructed by very strict rules in which everything is perfectly predictable from a simple formula.
The formula may be simple, but when the operation is repeated over and over again, a totally unexpected variety of shapes emerge. In particular, the images resulting from a set of numbers called the Mandelbrot set exhibit extraordinary complexity and self-similarity. The mathematics of fractals shows great promise for a wide variety of applications. But perhaps the most vivid application of this new geometry is found in undeniably beautiful computer graphics. Techniques based on fractals were used to generate the extragalactic special effects for the movies Star Trek II and Return of the Jedi.
Mathematics had its beauty, but the beauty was hidden, except for those who could work it out and understand in full detail what was happening to the formulas and to the equations. And now, thanks to fractal geometry, thanks to the computer, one finds that mathematics has another face, which had been quite unknown, unsuspected, which is this face of extraordinary physical variety and beauty.